All right, so in this video, we're going to continue our discussion with finding area bounded between curves. And so what we'll do here is we're going to try to find the area bounded between these two curves. And in part A, we're going to go with respect to x, and then we'll follow up with a part B and go with respect to y. So just like the last example we looked at, we want to always start with our graph. And so our graph is going to look something like this. Knowing that a y squared equals 4x, this is going to be a sideways opening parabola. So we're going to have something that looks like that. And then for this guy, this is just a standard line with a positive slope and a y-intercept of -4. So it's going to now do something like this. And these pictures, again, don't have to be perfect, but they do have to represent the actual region we're trying to investigate. All right, so the region that we're looking to investigate, of course, would be between them. So right here. And in this first part, part A, I'm pushing our hand a little bit and saying we have to go with respect to x. And so if we go with respect to x, that's going to be the top minus bottom mentality. And I think I told you before that a lot of times I like drawing in a vertical line, which helps me identify the top versus the bottom. So if I put that in there in blue, you can see the top now would be touching the parabola and the bottom would be touching the line. But in this particular case, there's a little bit of an issue. If I put my vertical line over here, let's say, now you can see my top is still touching the parabola, but my bottom is also touching the parabola. So what this actually means is that we're going to have to divide this up into two different regions. And where we're going to have to divide them is going to be at that red line right there. As my vertical line here, if I scan that across, you can see that on this side of the red line, I'm going to be top and bottom here. On this side of the red line, I'm going to be top and bottom on the line there. Okay, so the hard part is not so much figuring out tops and bottoms. In this particular problem, it's going to be finding the actual values where we're going to transition. And so essentially, points of intersection. So to find these points of intersection, I'm going to go ahead now and need to take these functions and set them equal to each other, which should give me x values. Okay, so if I'm going to get x values though, that means I need to have this guy solve for y as well. So y would equal plus or minus 2 root x. Now I'm going to take this curve and set it equal to this curve to find where they intersect, and that will give me my x values. So I'm going to take 2x minus 4, set it equal to plus or minus 2 root x. To solve this, I would end up squaring both sides, but before I do that, I think it's probably best, because of the 2 that's in common, we can divide that off just to make our numbers a little bit easier. So at this point now, I'll go ahead and I'll square both sides. That'll give me an x squared minus 4x plus 4 equals an x. Bring that x over. Go ahead, and it looks like it can factor an x minus 4 and an x minus 1. And so we'll get a 4 and a 1 for x. And those numbers make pretty good sense. In fact, this point of intersection here looks to be about 1. So that'll be my 1. And then this point of intersection here looks to be about my 4. So this guy here will be 4. Okay? So let's go ahead and get this thing set up now with respect to x. So we'll have two regions again. We'll have the first one going from 0 to 1. And for 0 to 1, the top part is going to be the top of this sideways opening parabola, which when you look over how we've solved, that's going to be the positive 2 root x. So we'll have a positive 2 root x minus the bottom. The bottom would now be our negative 2 root x. So minus a negative 2 root x dx plus the second one, which would now be our 1 to 4. On the interval 1 to 4, our top is going to be the top half of the parabola, so 2 root x, minus the bottom, which would be that line at 2x minus 4. Once again, a dx. So we've got our top minus the bottom plus the top minus the bottom. Again, the big minus the little. So in this particular case, we had to be really careful here to make sure that we did not get too presumptuous in what's our top and what's our bottom, understanding that if you go from left to right on the interval 0 to 4, you would change bottoms at x equals 1. That's why we had to set it up as two separate ones. Okay? Again, you can work this one out on your own. This one gives you a 9 for a final answer. But knowing that you have to work two separate integrals might give you an idea of hopefully finding an easier way. And so that's going to take us into part B now, where we want to integrate with respect to y. Okay, so now in this part, I guess it would be part B. I have part A listed. We'll call this part B. We're going to go with respect to y. And so with respect to y, I'm going to go ahead and sketch in a horizontal line. And if you picture that horizontal line now moving all the way up and down this region, from this particular value here, which is our point of intersection, to this other point of intersection, you're not going to change the right versus the left. On this entire interval, the right will always be the line, and the left will always be this parabola. So this indicates we're only going to need one integral, which would be far less to compute when it comes to working it out. And so when it comes to now putting this together, since we're going with respect to y, you have to remember we can only have y's in our entire setup. Okay, we can only have y's, which means we're going to need to take both of these and solve them for x. So for this first one, this is going to say that x equals 1 over 4 y squared, and this one is going to say that x equals a y plus 4 over 2. Okay, so if we only want y's, we have to solve those for x. So let me go ahead and get this set up, and then I'll circle back and look at our actual points of intersection. So the area would be the integral, and like I said, I'm going to come back and talk about these here in a minute. But the right being the line, would be this function right here, y plus 4 over 2 minus the left. The left would be that parabola, which would be this guy here. And then since we're with respect to y, it's got to be a dy. So again, remember, if you choose a dx, there can only be x's. If you choose a dy, there can only be y's. Additionally, these bounds have to also correspond with the variable that we're integrating with respect to. So this has to be a y equals a number and a y equals a number here. Just like the last problem, to find out where the points of intersection are, we'll take both of these and we'll set them equal to one another. So when I do that, that gives me a y plus 4 over 2 equals a y squared over 4. If I cross multiply, and simplify just a little bit, 2y plus 8 is going to equal y squared. Okay, so really what I did is I multiplied the 4 over, 2 goes into 4, giving us a 2, and then when I distribute the 2 there, that gives me this. We'll manipulate it a little bit more. Y squared minus 2y minus 8 equals 0. It's going to then factor into y minus 4 and y plus 2. And we get a y equals 4 and a y equals negative 2. The fact that one's positive and negative makes good sense based upon our picture. This guy would be our negative 2 and this guy would be our positive 4. If I drop those in now, my setup is complete. So again, one of the biggest things I want to emphasize in a problem like this is that if you choose to go with respect to a certain variable, that's great. But make sure that's the only variable you see in here. If we chose to go dy, we can only have y's, and these have to be y's as well. Okay? So when you integrate this, you get the exact same thing as you did in the last setup, but only now you have one integral instead of two that you would need to compute.